Now we'll add the main Python file for problem 0031, next permutation. Let's open the file and build the solution step by step. First, we import list for type hints. The permutations import appears here, but we will solve this in place without using it directly. Type hints make the method signature clearer. You can ignore the permutations import for this implementation. We'll wrap our algorithm inside the solution class to match LeetCode's expected structure. This class will contain our next permutation method. Define next permutation to modify nums in place and return none, as required by the problem. The method takes a list of integers and performs an in-place transformation. First, handle the edge case. If nums is in descending order, it's the last permutation. Reset to the smallest permutation by sorting ascending and return. Descending order means we're at the highest permutation. The next one cycles back to the lowest. Scan from right to left to find the first ascending pair. The index I1 is our pivot where an increase can be made. This condition identifies the pivot, the first place from the right, where we can make the sequence larger. Initialize trackers to find the smallest number greater than the pivot in the right suffix. We scan from the end to locate that best candidate. Min_IDX and min_val help us pick the minimal element larger than the pivot, so the overall change is as small as possible. Swap the pivot with that next greater element to make the permutation just larger than the original. This swap places the correct next greater value at the pivot position. Now we sort the suffix to be ascending. This bubble pass loop keeps swapping adjacent inversions until no swaps occur. We repeatedly pass over the suffix until it's sorted in ascending order. Swap neighbors when out of order. If a full pass makes no swaps, the suffix is sorted and we can stop. No swaps means the suffix is fully ascending, so we break out. Once the suffix is sorted after the swap, we're done. The array has been transformed in place. We return here because we've successfully formed the next permutation. Let's add a quick test. LeetCode expects an in-place change, and the method returns none. Running this prints none because the function modifies nums in place. Try inspecting nums after the call to see the updated permutation. Now we'll add the Python file, where we'll implement the longest valid parentheses solution. Let's open the file and start coding step by step. Let's start by noting the time and space complexity for this stack-based linear scan. No imports are needed for this approach. Now we'll add the solution class to match LeetCode's expected structure for Python submissions. Next, we define the method and initialize our stack. We seed it with -1 as a Sentinel base index to help measure valid substrings. The -1 Sentinel acts as a base when a valid sequence starts at index 0, making length calculation straightforward. We track the best length and count and iterate with indices. When we see an opening parenthesis, we push its index for future matching. Enumerating gives us both index and character. We use indices to compute lengths between matched pairs. On an opening parenthesis, we push its index. On a closing parenthesis, we pop to try to match it with a previous. Popping discards a matched. If there was no match, the stack may become empty, which we handle next. If the stack empties, it means this can't be matched, so we reset our base to the current index. Otherwise, we can measure a valid length using the current top. When the stack is empty, pushing the current index establishes a new boundary for future valid substrings. If the stack isn't empty, the top holds the last unmatched index. A minus that index is the current valid length. We update the maximum and return it at the end. This calculation stretches from the last unmatched index to the current I, giving the length of a valid window ending at I. Finally, let's add a quick test. For the string, the longest valid parentheses substring has length 4. Running this should print 4, confirming that our stack-based linear solution works correctly. Now we'll add the solution file, where we'll implement the rotated binary search. Let's open the file and start coding step by step. Let's start by noting the time and space complexity and importing list for helpful type hints. Now we'll add the solution class. Inside it, we'll implement a binary search adapted for rotation. Next, we declare the search method with type hints. We'll keep track of a moving left and right boundary. Initialize 2 pointers, left at the start and right at the end. We'll narrow this window until we find the target. These pointers define our current search window inside the rotated array. Set up the main binary search loop. We compute mid safely and immediately return if we hit the target. This mid calculation avoids overflow and centers the search window each iteration. If mid matches the target, we return its index. Otherwise, we check if the left half is sorted to decide where to search next. When a left value is less than or equal to mid, the subarray left mid is sorted. If the target lies within that sorted left half, we shrink right to mid 1. Otherwise, we search the other half. This condition checks if the target falls inside the sorted left region. If the left half isn't sorted, then the right half must be sorted. We then check if the target belongs there. This condition verifies the target lies within the sorted right region. Based on the check, we move left or right accordingly, discarding half the array each step. Adjusting the pointers is what gives us logarithmic time by having the search space each iteration. If the loop exits, the target wasn't found in any half, so we return -1. This is our not found sentinel value required by the problem. Let's add a test where the target exists in the rotated array. We should get its correct index. Now a test where the target does not exist. This should return -1. Finally, a small array to confirm edge behavior with minimal elements. Running these tests should output 4, -1, and 1 respectively, confirming O log n time and O1 space. Now let's add the main Python file where we'll build the step-by-step solution. Opening the file so we can start typing the solution together. Let's start by documenting the complexity and importing list for clean type hints. Type hints make our intent clear and help with editor tooling without affecting runtime. Now we'll add our solution class and the method that returns the first and last indices of the target. The signature states we take a sorted list and a target, returning a 2-element list of indices. Let's define a helper to find the first occurrence. Set left and right bounds, and initialize the answer to -1. These pointers bound our search window. First stays -1 until we see the target. We iterate while the window is valid, compute a safe mid index, and check if mid hits the target. This mid formula avoids overflow and splits the range to guide our search. When we find a target, we record the index and push right leftward to seek an earlier index. If mid is too small, we move left rightward. Capturing mid as a candidate, then searching left ensures we land on the earliest occurrence. If mid is too big, we shrink the right bound. Once the loop ends, we return the earliest index, or -1. This helper cleanly reports the first index found, or -1 if the target never appears. Now we'll mirror the logic to find the last occurrence, resetting bounds and initializing the result. We track the furthest right index where we see the target. Again, we loop and compute mid. When we hit the target, store the index as a candidate for the last position. We record mid and will bias the search to the right to find the final occurrence. To find the last, shifting the left bound right helps us continue searching for later occurrences. We return the last index from the helper, call both helpers, and package the answer as first, last. If the target is absent, both helpers return -1, yielding -1, -1. Otherwise, we get the correct span. Let's test a target that isn't present. The function should return -1, -1. For target 6, we expect the output to be -1, -1. Now test a target with duplicates. We should see the span covering all 8s. For target 8, the expected output is 3, 4. Finally, test an empty array to confirm edge case handling remains correct. Great! Our binary searches run in O log n time and use O one space across all cases. Now let's add the main Python file for problem 0035. Open the file, so we can start building the solution step by step. Let's start by noting the time and space complexity and importing lists for type hints. We import list so we can clearly annotate the nums parameter as a list of integers. Now we'll add the solution class. The comments summarize our approach and the method's purpose. LeetCode expects methods inside a solution class, so we wrap our algorithm here. Next, we'll declare the search insert method with type hints and a short docstring. This signature matches the LeetCode prompt. It receives nums and target and returns an index. Initialize 2 pointers for a half-open interval. Using right as len, nums keeps the upper bound exclusive. Setting right to len, nums allows inserting at the end when the target is larger than all elements. Now let's start the binary search loop and compute the midpoint of the current range. Mid splits the interval. This formula is a standard, robust way to compute the midpoint. If the midpoint value is greater than the target, we discard the right half by moving right to mid. Keeping a half-open interval, setting right to mid excludes mid and keeps candidates on the left. If the midpoint value is less than the target, we move left past mid to search the upper half. Advancing left to mid plus 1 narrows the search to values strictly greater than nums mid. If nums mid equals the target, we can return mid immediately since we found the exact index. This early return handles the exact match case efficiently. When a loop finishes, left is the first index where target can be inserted while maintaining order. This leverages the half-open interval invariant. Left always points to the correct insert spot. Finally, let's test with nums 1, 3, 5, 6, and target 2. The expected insert position is index 1. Running this should print 1, confirming our binary search insert position works. Now we'll add the solution file where we'll build the valid Sudoku solution step by step. Let's open the file and begin coding. Let's start by documenting complexity and importing lists for clear type hints. The typing import helps us express the board as a list of strings. Now we'll add the solution class that LeetCode expects. LeetCode creates an instance of this class and calls our method. Next, we'll define isValidSudoku with a typed signature and a concise docstring. This method checks rows, columns, and boxes for duplicate digits. We'll set n equals 9 and create 3 arrays of sets to track seen digits per row, per column, and per 3 by 3 box. Each position in rows, calls, and boxes stores the digits we've already encountered. Now we iterate over every cell. We read the value and quickly skip blanks represented by the. Skipping avoids treating empty cells as numbers. First, enforce the row rule. If the digit is already in this row, it's invalid. Otherwise, record it. Set membership is 1, so this row check is constant time per cell. Next, we apply the same check for the column to catch duplicates vertically. This mirrors the row logic, but for columns, still 1 per check. Finally, we map the cell to its 3 by 3 box using an index formula, then check and record duplicates there. Dividing row and column by 3 groups cells into the 9 boxes index 0 through 8. If we complete the scan without conflicts, we return true to signal a valid board. This is the all-clear outcome after checking rows, columns, and boxes. Let's try a standard valid Sudoku board and print the result. This call should print true for the valid board. Now test an invalid board that violates Sudoku rules and print the result. This call should print false, demonstrating our early exit on duplicates. Now we'll add the main Python file for LeetCode 0037 Sudoku Solver. Let's open the file and start building the solution step by step. Let's start by noting the rough complexity and importing default dict for sets, plus list for type hints. Defaulting lets us create sets on the fly for rows, columns, and boxes, which keeps lookups fast. Now we'll define the solution class and the solve Sudoku method and capture the board size n. The method receives the board and solves it in place, so no return value is needed. We'll prepare 3 hash sets to track used digits per row, column, and 3x3 box, then scan the board to seed them. These structures let us validate choices in O1 by remembering which digits are already used. Empty cells are dots, so we skip them. For filled cells, we parse the digit and mark it present in the row. We only seed constraints from cells that are already filled in the given puzzle. We also record the digit in its column and corresponding 3x3 box using a simple index formula. Box index. Rows and columns are grouped by 3. This maps each cell to its box 0 through 8. Next, a helper checks if a candidate digit conflicts with constraints from the row, column, or box. Valid means the digit is absent from all 3 constraint sets for its position. Now, the backtracking search. If we pass the last column of the last row, we're done. If we finish a row, wrap to the next row. This base case signals that all cells have been processed successfully. After wrapping, advance to the next cell. If the current cell is already filled, skip it and move right. We only search choices for empty cells. Pre-filled cells are constraints to honor. Compute the box ID for this position and iterate over digits 1. 9, pruning immediately on invalid candidates. Trying digits in a loop is the core of backtracking. Invalid ones are skipped fast. Place the candidate. Update all 3 constraint sets, then recurse to the next cell to continue the search. This is our tentative choice. We try it and only keep it if deeper recursion succeeds. If recursion returns true, propagate success. Otherwise, undo the placement and all related set updates to backtrack. Backtracking means cleanly reverting the board and constraint state before trying the next candidate. If no digit works in this cell, we signal failure for this path. Finally, we kick off backtracking from the top left cell. The solver starts at row 0, column 0, and explores until the puzzle is solved. Now let's add a sample Sudoku board to solve. Dots represent empty cells that our solver will fill. This is a standard 9 by 9 Sudoku input, represented as a list of lists of strings. Here are the middle rows. Each sublist is a row of the Sudoku grid. Notice how given digits constrain the search, dramatically cutting down the possibilities. We close the board and call Solve Sudoku. It modifies the board in place, so printing the call returns none. Run this to solve the puzzle. Inspect the board variable afterward to see the completed solution. Now let's create the Python file where we'll implement and explain the solution. Opening the file so we can begin coding step by step. Let's start by noting the rough time and space complexity, then import defaultic for counting and row_cache to memoize our recursive function. Row_cache will remember results of count and say for each n so we don't recompute the same sequence. Now we'll define our solution class to group related methods cleanly. Encapsulating logic in a class mirrors how LeetCode expects Python solutions. We'll create a helper RLE method that performs run length encoding on a given string. Temp accumulates the encoded result, and frequency dict tracks counts for the current character. RLE transforms something like 111,221 into 312,211 by describing counts of consecutive characters. We start by counting the first character, then iterate from index 1 onward. When the current char differs from the previous, a run ends. This loop scans the string once, detecting boundaries between consecutive character runs. On a boundary, we flush the previous run by appending its count and char, reset that count, and start counting the new character. This is the core of run length encoding. We write the count followed by the character. If the character is the same as before, we keep counting. After the loop, we append a final run that didn't get flushed inside the loop. This post-loop step ensures the last run is included, since the loop only flushes when a change is detected. We return the encoded string. Next, we decorate count and say with _cache to memoize the sequence for each n. Memoization avoids recomputing earlier terms of a sequence during recursion. Now we'll define count and say. The base case is n equals 1, which is simply the string 1. Every recursion needs a base case. Here, it anchors the sequence. For n greater than 1, we compute the previous term recursively and run length encoded to get the current term. This single line captures the recursive definition. Describe the previous term to form the next. Finally, let's add a quick test to print the fourth term of the sequence. Running this should output 1211 for n equals 4, 1, 1, 1, 2, and 2 1s. We'll create a Python folder to organize our combination, some solution, and tests. Now we'll add the main file for LeetCode 0039, combination sum. Let's open the file and build the solution step by step. Let's start by noting the backtracking complexity comments and importing list for helpful type hints. This import lets us annotate lists of integers for clarity. Now we'll add a backtracking solution class and define the combination sum method that returns all valid combinations. This method receives candidate numbers and a target and returns all unique combinations that sum to the target. We keep an accumulator list called result, declare a nested backtrack helper, and begin with the exact sum base case. Result will collect every valid combination we discover. If the remaining sum is 0, we found a valid path and copy it into results. If we overshoot below 0, we prune that path. This check stops exploring branches that already exceeded the target. Otherwise, we iterate from the current start index to avoid permutations and tentatively choose a candidate by appending it. Starting from start ensures combinations are built in non-decreasing index order, preventing duplicates. We recurse using I again to allow unlimited reuse of the same value, then undo the choice. Finally, we kick off the search from index 0. This initial call starts with an empty combination and the full target. We return all collected combinations. Next are complexity notes for a bottom-up dynamic programming approach. The backtracking method outputs all valid, unique combinations. Now we'll add a bottom-up solution class with the same signature using dynamic programming. This version builds combinations for all sums up to target using tabulation. We create a DP table where DP, I, holds combinations summing to I, seed DP0 with an empty combo, and iterate target sums from one target. Each entry is a list of lists, all unique combinations that reach that sum. For each candidate that fits the current sum I, we look back to combinations that compose I, nums, j, and extend them. This guard ensures we only use candidates that do not exceed the current target sum I. We build a new combination, sort it to canonicalize order, and check for uniqueness to avoid duplicates. Sorting ensures 2, 3, and 3, 2 are treated the same when checking for duplicates. If it's new, we add it to DP. After filling the table, we return all combinations for the final target. The DP result corresponds to all unique combinations that sum to the target. Test 1. A classic case where 7 can be made as 7 or 2, 2, 3. We call the latest solution class defined, which is the DP approach. Test 2. Multiple paths to 8 exist like 3, 5, and 2, 2, 2, 2. This input explores combinations that sum to 8 using different candidate counts. Test 3. With only candidate 2, there should be no combination that reaches 1. These tests print the results using the DP implementation we defined last.